Hello everyone, we'll be looking at examples and developing analysis tools for MapleSim models. In this presentation we'll be taking a look at two different models. We'll begin by looking at a 5 degree of freedom robot model and considering how we can investigate this model further by examining how changing link lengths inside the robot and perhaps also a controller gain, how they affect the overall behavior of the system, and get some general insight into the model itself. We'll also be taking a look at a second model. In this case, we're looking at a bit more of a fun model. This is a Trebuchet model, where we're going to be launching a projectile, and we'll be able to try and maximize the distance that the projectile can travel. And we're taking a look at some of the design characteristics for this particular component and understand what the effects are if we change lengths, angles, as well as some of the mass properties that we're interested in. So without further ado, let's jump right into our first model. So here we have our 5 degree of freedom robot model. This is one of the models right out of the examples. We can access this particular model by going to Help, Examples, and under the physical domain multi-body, we have the 5 degree of freedom robot model. I've taken that model and I've modified it just slightly, so that the links themselves have been parameterized. So here, if I take a look at link 1, I provided the length for this as L1, and similarly for link 2, L2, and for L3, L3. And I've created a parameter block where I've parameterized these values. And this allows me to make it so that each one of these parameter values can be changed in the model, and as a result update what the characteristics are for each of these lengths. Additionally, I've removed the default probes that come with the model and added one probe at the end of the end effector. And what I'm interested in doing is finding out what the X, Y, and Z positions are as the robot moves in space. So I'll start simulating the model here. And while it simulates, I'll give you a bit of a sense of what's going on. We have our servo motors that are connected to the different joints. In this case, we have multiple revolute joints. And those servo motors will actually drive the robot system. So here we can see our simulated results. And we can see those servo motors controlling the robot arm. As we can see in our 3D view, it's articulating in space. And the entire system has mechanical characteristics allowing for any of the effects such as the end effector moving up and down to have results on how the mechanism deflects. As you can see in the body here, there's some deflection. And that probe that I've added to the end effector, I can take a look at the X, Y, and Z positions just in our plotted results. And these also include a time matching line. As the 3 animation is being played, I can see the time matching for each one of those positions. Another graph that I can create, which I've created in advance, is a Y versus Z plot. So here I have the Z position of that end effector and the Y position, again, of the end effector, plotted with respect to each other. And when I play the animation, I can see that there's a little dot here that translates along the different plots and shows me exactly where it is in space. And so what I'm going to do is I'm going to use this as my baseline curve, and I'm going to start changing things such as the length for this one, so this is link 1, and the length for this one, this is link 2, as well as a controller gain that's going to be used at the base. And we'll do this using a programmatic approach, and that's going to be using a Maple worksheet. So to add a Maple worksheet to my model, I can go over here to where my templates are and find worksheet, double click that, and it'll ask me, do I want to create an attachment, and I'll call it worksheet 1. That's a perfectly good name. And that'll open up MapleSim, our Maple worksheet that's connected to MapleSim. And I can even see here at the very top a bit of a preview window linking back to my MapleSim model. And I can start typing in my Maple API commands that connect these two together. So by running the first command here, I've actually linked this particular variable A to my MapleSim model using the link model command. Of course, calling A, now I can say things like simulate, and this will actually simulate the model just like we did earlier, only using the Maple worksheet itself. And so what I'm going to get back are 3 plots that show the X, Y, and Z plot, just like we saw earlier. I can also take a look at other characteristics. So if I want to take a look at the particular parameters that are available, I can do that, where I can say get parameters. And I'm going to find out what the parameters are for this particular model. So here I can see that I have multiple controller parameter values. So KD 1, 2, 3, 4, and 5, as well as KI 1 through 5, KP 1 through 5, and my link lengths, so L1, 2, 3, and 4 in this case. And these parameters relate back to, if I go to the MapleSim model, the values seen in my parameter block. So here are the controller parameters that I see in my worksheet. And here are the robot link lengths that I have in my worksheet as well. Let's go back to our Maple worksheet, where we can see the results we were looking at. And the next thing we can take a look at is getting a compiled version of our model. So we'll call this cproc, and we'll use the API called getCompiledProcedure, and we'll pass the params equal to. Let's take a look at, in this case, L1 and L2. And also let's grab our other parameter here. Let's grab one of the controller values, KP. And we'll just make that fix here. So what we're doing is we're actually getting the compiled version of our MapleSim model that has now just been returned. And this allows the model to run just the integration process of our compiled procedure and not have to develop the whole compiled procedure each time we want to be able to simulate, like we did with the simulate command. We can directly just get our results, and this allows for much faster computation. We can also interrogate our get compiled procedure, so we can say things like get outputs to see what kind of outputs we're going to get. Here we can see our probe 1, 2, and 3, so relating to the X, Y, Z values, just like our simulate command above. And also we can say get parameters for our compiled procedure, and what we'll see is our reduced subset, so in this case our 3 parameters that we specified, instead of the large list that are available when we use our simulate model. And of course, if I want to take a look at the floating point version of that, so rather than looking at the fractions, I can say eval the previous line. That's what the % sign allows me to do. And so I can see what my floating point version is of that model. So that's great, but now I want to be able to actually simulate my results and get some information back from it. So that's possible by simply calling our compiled procedure, and we can specify our values that we're interested in. So in this case, we directly provide those values, and I'll just use the same values that are in our default window here, and I'll use params to make it work. And what we get back, actually, instead of a set of plots like we saw with the simulate command, we get back matrix data. And what we can notice is that the matrix data that we get back actually has 4 columns. And what the difference is here is that our first column is time, our second column is our first probe, in this case it's going to be the X location, and then the third column is our Y data, and the fourth column is our Z data. And I wanted to be able to make something like my own procedure where I can create the results from this and put it into a plot. So I can call that, and I can say myproc, and we'll define it as providing and the values that we've grabbed from above, so L1, L2, and KP1. And we can say we want to define this procedure to be able to run this cproc and generate a plot that we're interested in. So I can just reuse my command here, and I'll give it to a local variable, call it results, and I'll actually use the parameter values instead of the numeric values. This way, when I call my procedure, the values for L1, L2, and KP1 will be passed into the compile procedure. And what I want to return is the plot results. And in this case, let's try and create a plot similar to, if we go back to our analysis window, to this YZ plot that we see here. And so we can take a look at if we can change any of those values, L1, L2, and KP, what kind of effect we can have on this particular plot. So to do that, we want to be able to get the results, and we will take a look at the data from our columns, just like we saw here. This is going to be column 4 and column 3. And we'll just finish that off. And so there we now have a procedure that's defined that will give us the results we're looking for. And I should be able to get plotted results just like we saw in our simulated window. So that seems reasonable, but we want to get into something a bit more interesting where we can start interacting with the model and be able to explore some of the capabilities of what the model does. What happens if I actually start changing L1, L2? So there's a nice quick command called explore that Maple provides, and you can pass in your own procedure into this, and we can say our parameters that we're interested in. And what this will do is actually launch a building window that will allow you to develop the interface for your explore command. And I can quickly specify some of the parameter ranges that I'm interested in for the values, and nicely place some of the components. Let's just go with on the left-hand side, and we'll take a look at what this does. So this is going to generate a plot because it's going to use our procedure we defined before on the side here. But what you'll notice that's different is now we have sliders that relate those values, KP, L1, and L2. And when I adjust these sliders, I can actually see the difference. So this is actually changing the behavior of our simulation. And I can see that there's certain regions where I get responses that I'm interested in. And if I adjust it just right, I can also start identifying areas where perhaps my model becomes unstable, where you can see there's a high degree of vibration. And let's see if we can emphasize that even more here. So we can identify what happens if I start changing these lengths on our robot significantly. Will this change the behavior of my system? Will the system become unstable, or is it going to move into areas that I'm more interested in? Or in fact, another area it could be is my system insensitive to these variations, and the values for some of the components aren't so critical. So this is a nice way to just use the explore command to quickly create this structure. But what if we want to go and create this on our own? Well, we absolutely can do this. And what we use is one of our package tools called document tools. And what this will load is the document tools provides the capability to connect to our components we see here on the left-hand side. These are components such as the plot component and the slider components. So we'll just add those in. And so we can make it so that these 4 elements will then be operating just like our explore command we saw here. So let's go and modify our procedure. Let's go back up to my procedure. And we'll use this as a starting point because the behavior is the same that we're looking for. And if I take this, and I'm going to call this my procedure 2, and what I would like to do is instead of just returning the plot, I want to update the plot element here. And so I can right click on it and find out what its name is. So this is called plot 1. And I can copy that, and I can say I would like to set properties for plot 1, its value, and I want to use the exact same plot command as I did before. And that now will allow me to, instead of just returning the plot, we'll actually set the properties for plot 1 to that value. The next thing that I want to do is get the values for L1 I'll do this sort of as a local variable, as well as L2 and KP1. And I can do that simply enough by using the other command. Instead of set properties, we're going to use get properties. And I'm going to take a look at what these slider components are. So this one here is called slider 0. And so I can say slider 0, and I want to get the value of that. And then of course I can quickly repeat this for L2, and I can call get properties. And the last parameter that I'm interested in is going to be KP1, and I'll do the same thing. And I know that the order for these, slider 0, 1, 2, are going to be sequential. That's the nice thing about Maple, is that it will add these automatically sort of sequentially for me. So I can see here that the last one is going to be slider 2. So now that I'm actually going to refer to these slider elements and get those values, I no longer need to pass them into my procedure, and I can execute that procedure, and so now it's properly defined. Before I run my procedure, I would want to make sure that my ranges for these values are going to be in the reasonable range, and I can do that simply enough by starting with my slider here. In this case, this is going to be for L1, so we can give it some reasonable values, as well as I can provide some tick mark values that I can show, and you can see that be populated on the slider value here. Of course, I can repeat this process for the other slider. This is going to be now for my link 2, and do the same sort of process where I can show the label and have it appear on screen. Do the last one really fast. This is for KP, and we'll make it so that this one has a slightly larger range for our axes. So now we have slider values that are going to be values that are somewhat valid for our model, and that we're interested in a range that we're interested in for each of these. We want to be able to make it so that as we adjust these, we can see here nothing's happening. But if I just simply call my procedure and I go back up here, I was able to get the result that I'm looking for, where the values are read from the slider and the plot is updated. If I want to make it so that this happens every time that a slider value is changed, I can copy this command, calling my procedure, and embed it underneath these components. So I'll expand the edit value, and you see here there's some document tools and information that's pre-populated. I'm going to just simply replace that. And so that's for slider 0. I'll quickly do it for the other ones. And what this is going to allow me to do is allow for any time I make a change to any of these sliders, that procedure will automatically be called and the graph will be updated, or I should say the plot will be updated. So we can see here, as I'm adjusting the value for KP, we see the same behavior we saw above. And if I start adjusting the slider for L2, again we see the same type of behavior. And of course the last one. Now one thing you'll notice is that if I move the slider around, I'm not getting any change in my response. If I want to make it so that I can do that, I can go back to my component properties and say update continuously while dragging. Turn that feature on. And what that does is, as you see here, I'm dragging my slider around and the plot's being automatically updated. This is a fantastic capability, particularly for procedures that are quite fast. And in comparison, if I run the slider without that feature enabled, you'll see that nothing happens. But in this one, it's fully enabled. If I want to go and create this sort of table look and feel, that's pretty simple enough. I just say insert table. We'll give it a single row. Maybe if I resize the table a little bit, I can even do things like some of our centering. This allows for some of the format capability that you might have, and I'll cut and paste my different elements. And by cutting and pasting, I don't lose anything like the name reference or any of the procedure commands that I've spent time developing. So now these sliders have simply just been relocated here, and I can even do L1, L2, and KP1. And as you can see, the behavior that I'm looking for is very much similar to the behavior we saw up above, where I can simply drag in the slider components and get the graph to update in both cases. So this is a bit of an introduction to kind of give you a feel for what it's like to use some of our embedded components, so the sliders and the plot graph, what it's like to write a procedure to get the kind of interface that you want to be able to play with some of the variables and see what happens when you plot those results. Some of the commands we see are document tools, and also our API commands such as get parameters, get outputs, get the compiled procedure, and of course simulate and link to model. These are all of our building blocks that we'll use for more complex examples, and they become our foundation for any of our more rich analysis work that we might want to do. So let's go and take a look at one of our other models. Going back to MapleSim, here is the Trebuchet model. And I'll get this simulating while I give a bit of a description. So in this Trebuchet model, what we're actually using is an investigation to find out how far we can launch our projectile. Some of the considerations we have are the dimensional characteristics for this particular model, as well as some of the components that we've included that are kind of interesting are the contact library found inside our multi-body. So we're using some of our contact characteristics to relate the sling contact with the ball and the peg contact with the sling holder or the retaining ring. So here we get the visualization of our system come up, and let's just run the play window. So we can see here our trebuchet launches that projectile and seems to go pretty far. So let's try and pan around here so we can take a look here. If we play that again, we can see the projectile moving, hitting the ground, and then bouncing as it's modeled to have a spring damper type contact behavior for when it hits the ground. Some of the things that we're interested in with this model are I'll get a little zoom in here. The peg itself has this particular ring that's going to slide off of it, and what angle we put that peg at and also how long we put that peg has a very non-linear effect on how the sling releases. So I'll play it a little bit slower here so you can hopefully see it. So you can see how the peg itself affects what angle the ring comes off, and then as a result how the sling is detached, and then now of course define the angle that the ball is released at, and then as a result affecting things like how far it goes, how high it goes, and those kind of characteristics. The ring itself, as mentioned, is using a contact characteristics between this peg, and then the sling actually uses multiple discrete contact characteristics for a rectangular plate to a ball. So we can get a reasonable approximation as to how the ball will actually come off the sling and go flying through the air. Of course, some of the plots we have are the position for how far away the ball goes, and also the position for where the trebuchet mechanism itself goes. So what we're interested in is to find out where this first point is that hits the ground and try and see if we can make that as far as possible. So in this case, we've already pre-made our worksheet, so we don't need to do it from scratch. This is also showing a little bit of some of the other features we have. So I'll scroll down, and some of the capabilities are all packaged under some of the buttons in this case. And so you'll see, just like our previous worksheet, a bit of a preview window into the MapleSim model. In this case, we've also included an image to give the user who's doing the analysis work a sense of what the different values are they are adjusting. So here we have the diagram showing L1 and L2, MC and MP. So we have L1 being the long arm, L2 being the short arm, based on the diagram, the projectile mass and the counterweight mass. And one of the areas that's a little bit more complex because of the nonlinear characteristics are going to be the peg length and the angle, as seen here in our diagram, that the peg is actually resting at. And of course we can simply take and plot our results with our first set of configuration, We can even include some highlighting with where's our maximum values by simply taking a look at the data we get and taking the maximum value, and also finding out what our maximum distance is by noting the first contact point with the ground. Of course, we can start playing with some of our sliders, changing the sizes of our projectile, its counterweight, and even for instance, like the peg, and simply run those results again and plot them on top of each other. And we can see here that there's a significant diminish in performance, where the distance is now only about 20 meters as opposed to our almost 46 meters that we had before. And then of course there's some things you can say, well, I'll just increase the counterweight mass and try again. Perhaps some of the other characteristics aren't as important, but you'll see that there's actually a lot of nonlinear correlation between these, and there does seem to be a significant effect. So let's say if we have a value in our design that we're interested in, and we want to be able to compare what those are. We can set up our values to something that we're interested in to begin with. Let's say we'll move it to 0.11. And let's say we want to investigate one parameter on its own and find out what the characteristics are if we just sweep through that particular parameter. So here we have our peg angle set at 0 degrees. You can see that's a pretty measly distance that we launched at. Kind of went up pretty high and then fell to the ground. And let's say if we go in increments of 4 degrees, what happens to our overall result? Well, we can immediately see there's a huge difference in our performance by changing that peg just a slight bit of an angle. So there is something quite important with the angle that we're looking at for that particular peg. But if we start increasing the angle a little bit more, then what we'll notice is that the difference between these results isn't as significant as we saw before. And we'll just take a look at a couple more values here. So for instance, if we go up to 12 degrees, we barely see anything. I'll just skip up to even our maximum on our scale here. And our maximum now actually is going to result in an angle that has a little bit less height than our other values. We can see here, and a little bit less distance. So this already shows us that our sweet spot is possibly between 8 and 16 degrees, somewhere in there. Maybe even including 4 with this configuration that we have here. So if we want to be able to do this type of analysis, we definitely can, and we can also do it on other characteristics. So if I say, let's plot this configuration here with a really short peg, we can again see a very measly distance that was traveled. And if I go and change it to, say, increasing it 10 centimeters, our peg length, again we can see there's a very big difference in response just by a slight change in some of our dimensions. And this will go, of course, only so far, and then when we get into say about 0.31, I believe is about when we start seeing diminishing returns again, and we're no longer in that sort of sweet spot. The nice thing about this type of analysis is that it can provide a lot of excellent model insight into what our particular system is. Are the variables that we're using, are they reasonable? Are they in ranges we can check to see if they physically make sense? Are they values that we can actually achieve? Perhaps it doesn't make any sense to have a peg angle that's 45 degrees. Maybe you can't physically do that. So perhaps you have to have a bit of a sanity check and make those adjustments in your model. Other areas where we can, of course, consider in our model is if we have a very large variation in the payload that we're interested in. So these are variables that we may not have any control over, and we might have to see, well, what kind of difference do we expect to see in our results? So here, if I change, say, the projectile mass quite a bit, well, I can see a very big difference in the desired outcome or the expected outcome from this particular system. This is a good way to get some just general feel for what your model is capable of doing, and it's a fairly manual approach. Of course, there is a programmatic way you can do this, and I'll refer you to our MapleSim command under analysis, and we have a command called parameter sweep. In this case, instead of going into it with a lot of detail, perhaps that's for another webinar at a later time, but I'll scroll down to some of the capabilities it has where we can quickly plot the results of multiple simulations over top of each other and get a sense of what different parameters are doing with the model. Another thing that's really nice with this command is it makes use of parallel computation. So we'll actually run each one of these simulations on the different threads of your computer so you can get your results back much faster. So hopefully that gives you a good sense of what it's like to create some of these types of analysis tools, a good sense of getting some of the API commands, which we can even see here are underneath the components, such as the buttons here we saw earlier, like link model, get parameters, compiled procedure, and being able to update some of our embedded components, such as our plot window. You should be able to even see some of that, where we can say our plot commands are being used here, being able to do set properties on some of our components, and get a sense of what it's like to build an interactive worksheet that links back to a MapleSim model and gives you some real insight into what it is that you're trying to do.